All right, here we're on 5.3 on linear programming in two dimensions, a geometric approach. So we're going to work some exercises from the book. So first one says we're supposed to maximize p equals 30x plus 12y subject to 3x plus y less than or equal to 18 and x and y both greater than or equal to 0. So first things first on these, we have to solve this for y, and so we're going to say y is less than or equal to minus 3x plus 18. Okay. Now with this, we know that it's going to be in the first quadrant, and so we're going to be over here somewhere. And now we have at 18, we're going to have a point, and then we're going to go down three, right, or down three, right one, and so on. And so it's going to look something like that. And we know y is less than or equal to that, and so we're going to be in this region right here. Okay. Now again, it goes further. The line keeps going up and the line keeps going down here, and we have the normal axes. But this is really all we're looking at. And so now with this, to maximize this, what we have to do is we have to find the 3 points. And once we have those, we plug them back into our profit function up here, P, and see what the max is going to be at which corner point. Okay. So with this one, what do we know? Well, that's going to be what? 0, 18. Now, if we plug in 0 for y, we're going to get 6 for x. So that's going to be 0, 6, or 6, 0, sorry. And then this is, of course, 0, 0. All right. So those are our 3 points. And again, we're just plugging them into p. So p again is equal to 30x plus 12y. So for the first one, let's call this 1, we'll call this one 2, and we'll call this one 3. For 1, we have basically p is equal to 0. Okay, so not very good. So unless we get some negatives, we're not going to use that one. Now here, let's plug in this one. So 30 times 0, and then plus 12 times 18. Well, 12 times 18 is equal to 216. And for the third one, we have p is equal to 30 times 6, and then we have plus 12 times 0. Well, 30 times 6 is 180. And so in this case, our max is the 216. So the solution is the max P is equal to 216 at, and then we're going to have the point 0, 18. Okay, so that's going to be our max. Now, if for some reason they'd ask what is the min value, of course, well, that's going to be 0. But they ask what is the max, and so that's what we have for our solution. And this is how we work these graphically. So we plot the inequalities, we find out what region is the feasible region, find the corner points, plug the corner points back into our maximize or in case minimize function, and then see which one fits the bill. Okay, so in this case, the 216. All right, what about another one? Now that we've got this down pretty well, hopefully, now again, we're going to solve for y. So y is going to be what? Well, y is going to be greater than or equal to minus 4 over 7x, and then plus 28 divided by 7 is going to be a 4. All right, and again, constraints there. And so if we plot this, again, it's going to be just the upper right quadrant. And so here's our 4. And so we're going to go down and right. And so it's going to do, something like that. Now, to scale, no, it's not to scale, but that's what we're looking at. And now this one says it's going to be greater than that. So that means we're going to be out here. Okay. And that's good because usually when it's unbounded like that, we need to minimize something, and that's what we're going to do. And so we're going to minimize. And so we just need to find this point and this point. Well, this point we know is what? Well, that's 0, 4. Now, if we plug in this one, okay, well, if we plug in 0 for y, and then x is going to be what? 7. So that's going to be 7 comma 0. So those are our 2 points. And so what we're going to do is we're going to look at our cost function, which is the 15x plus 25y. And so for 1, I don't know, let's call that one 1, and let's call that one 2. For 1, our cost is going to be what? 15 times x, which is 0, plus 25 times y, which is 4. So that equals 100. Now for 2, our cost is going to be 15 times 7 plus, and then 25 times 0, and that's going to be 105. So if we're minimizing this, this is going to be our minimum. So our minimum C is equal to 100 at, and then we have the point, what is it, 0, 4. Okay, so that's going to be what we have for our minimum cost at the point there. All right, so let's stop there and we'll come back for some more.